Morning, everybody. Thank you for making it out. I'm Christopher Gervais. I'm going to be speaking about automating infrastructure, primarily using Ansible, but the principles apply to just about anything. There's a number of tools out there that will do this. We'll touch on some of them briefly, but we'll go a lot more in depth into Ansible because it's multi-purpose, can do a lot of things. So just a bit of brief background. So some partners and I started Consensus a couple years ago. We do a lot of Aegir-based hosting, so that's Drupal hosting on a Drupal-based system. And we're all sort of open source programmers and sysadmins. So this kind of informs what you're going to see in some of the presentation. There are plenty of commercial applications and stuff that can do some of these things. We insist on pretty much an open source stack top to bottom. So we work primarily with educational institutions, nonprofits, and governments and other NGOs. So that leads to a bunch of interesting, at least interesting from my standpoint, use cases that are outside of what I've normally seen in the commercial space. So if you're just doing general web development, the relatively simple example that we're going to show should probably be more than sufficient for what you're looking at doing. We have worked with very large organizations that require like 5 nines uptime and stuff like that. We're not going to be covering that level of detail, but the infrastructure we use would support that kind of use case. More recently, we've been doing a lot of work with, say, Health Canada, for example, where we don't really have control over the systems that we're running our applications on. So what we're doing in terms of infrastructure as code is primarily building a replica of the system that we're working on so that we can use that as our staging environment to make sure that all of our configuration and testing and stuff can happen isolated from the production environment. So that's sort of the use case that we're seeing most recently, most often recently. For a lot of the nonprofits, it's a little bit more sort of standard Drupal development. Obviously, we use Aegir for it because that's our sort of tool of choice. So that's a simpler use case. Generally, we're talking about there just building a few VMs, wiring them up to be able to talk to each other and so forth. We won't go into a lot of detail, but I'm happy to talk about it more later if you like. So to give you a brief rundown of what the agenda is going to be this morning, we're going to start looking at sort of cloud computing in general, how we got to this point. I was tempted to go back to the abacus, but I only went back to mainframes and stuff like that. So I didn't. It'll go quickly through that just to get you an understanding of how we got to where we are. Then we'll look at some of the general principles of infrastructure as code, how it works, why you're trying to do it, what the mechanisms are. Then we're going to look at Ansible specifically and how that supports using infrastructure as code. And then I'm trying to leave pretty much the last half to do a demo and just walk through actually building a small VM on a cloud. Here in Canada, using guys by the name of Cloud A, who are out of BC, and they use OpenStack. So again, trying to keep to that open source and free software for the entire stack. So none of my presentations would be complete without an XKCD. So here we have the general idea of what we think we're going to get into when we do automation, right? We've got some task, doesn't take a lot of brain power, takes a bunch of time, so let's write a script or something to that effect for it, and then we should be able to have all this more time for the creative, interesting parts of our job. For me, the creative, interesting parts of the job are doing this kind of stuff, and so I really live in that ongoing development curve over there. But there's one of the things that I find interesting about this idea, right? I think people will, in general, sort of agree that this is how it feels. But in fact, I think we are actually closer to the top in that as soon as we've automated things, we just start taking it for granted and don't even notice the time that we're saving. And so we always feel like we're working on some new things and adding new features and so forth. But in fact, most of the time we are actually recouping quite a bit of benefit out of it. Of course, XKCD is great for a lot of other things. And one of them is this interesting sort of graph that shows essentially based on the amount of time that you're saving in your task by automating it, and how frequently you do that task, you can figure out how much time it's worth investing into the automation of this task. So for most of our infrastructure as code stuff, we live sort of towards the bottom middle. So it would take between an hour and 6 hours, and we would be doing this on a weekly or monthly basis, building new VMs, tearing them down, reinstalling them, things of that nature. So that gives us, according to this graph, somewhere in the vicinity of 2 weeks to 2 months worth of development time to write the automation that would go into this. Now, as it so happens, this has been happening, like I've been working on these kind of things over the course of several years. So not dedicated to doing just that, but I'd say we're probably in that 2-month range in terms of the amount of effort that we've put into automating this stuff. Now, again, we're working with relatively complex projects and infrastructure that we're trying to support. Plus, the workflows that we go through are sometimes out of the ordinary. Like I said, sort of replicating a production environment, having to rebuild that environment regularly, and so forth. So we're definitely in the black in terms of how much effort we've saved, and it gives us a real sense of confidence that we can go into developing really anything, and because it's in these throwaway cloud environments, we can, and it's efficient and easy and fast for us to tear them down and build them back up from scratch. There's not a lot of investment in each one of those things. We're investing in building out the overall application, which includes all of this automation of the infrastructure, rather than spending time going and mounting a new volume into a VM or something to that effect. So going back a bit and trying to just get some perspective on where cloud computing is today and where it's coming from. Way back at the very beginning of what would be roughly modern computing, we had basically time-sharing systems. So these were enormous building-sized computers, usually only at sort of academic or government institutions. So the Department of Defense might have some of these, universities would have some of these. They would be doing complex calculations, what were at the time considered complex calculations. These days you can do them in, on your watch, basically. But at the time, doing things like ballistic calculations and things like that were difficult to do, and that's where this came from. These buildings had terminals that you would be working at, so you can see what looks like a screen. That's not actually a screen. It's a bunch of switches. So there weren't actually screens at this time. And it was one massive computer that people would be able to interact with, usually one at a time. The time-sharing aspect came in relatively quickly, and you were able to run multiple workloads on it at the same time. So this is actually not that far off from what we're seeing now, just decades later. Then the computation technology got a whole lot cheaper, still incredibly expensive, and not something that anyone outside of institutions could deploy. So here we would be talking about banks, we would be talking about insurance companies, organizations that are crunching lots and lots of numbers. As this progressed, those were sort of the leading edge. Then what happened was large enterprises started acquiring these to do their internal accounting systems, HR, and things like that. So again, very big machines. Generally, in this case, institutions would be using them, would have them installed on site. And you would have operators that were dedicated to doing nothing but interacting with these systems. Okay? Fast forward a couple of decades, and now companies are able to now start deploying their own servers. Now servers look a little bit more like this, so they're basically a box, pizza box-sized system. They would install racks. These would be usually on-premise in a computer room or something like that. Companies would be using them to, for example, run their own email servers. This was a popular model through to the turn of the century. Following 9/11, just to let you know, this started to decline significantly because people felt that they were a target potentially, especially larger enterprises, that if you had all of your data on site, and that data got destroyed in some fashion, your building got blown up, because that was the paranoia of the time, you would lose all of your data. And so off-site storage and things of that nature became more popular, and that's where data centers really started to take off. And data centers basically aggregate all of the computing capacity into dedicated data centers. So dedicated buildings with specific HVAC systems, so all of the fire suppression, keeping everything cool and dry, things of that nature. And then also having very big pipes to the internet. So this is where the internet was really starting to take off. And this would have been right around that turn of the century where the dot-com bubble started to really pick up. And so at the time, there were lots of companies that thought, for example, that you would order pet food online and have it delivered to you monthly or something like that, right? And there were all these startups that were investing heavily in computing capacity. Now, these days, that kind of thing seems like a reasonable service for somebody to subscribe to, right? We're used to buying stuff online. At the time, that was not the case, and it was a huge crash. And what that resulted in was all this immense computing capacity sitting there idle. And at the time, companies like Amazon bought it up at a discounted rate. And around that time where data centers were really starting to pick up, basically between the server room and data center point, virtualization started to kick in. Now, virtualization basically just takes a big system, say one that has, say, 8 processors and 32 gigs of RAM. That's an enormous server to do the vast majority of workloads that you might need to do. So rather than have one big system that's sitting idle most of the time, you basically just run a lot of virtual machines on there where you've got an entire operating system running, and you can run a bunch of those in parallel on one of these big beefy machines. Data centers were all about virtualization. You could have dedicated systems, but virtualization was by far the most popular and remains the most popular model, and is actually the basis of cloud computing. So when you go to an Amazon or an OpenStack provider or Google, GCE, those kind of guys, what you're doing is you're renting a virtual machine in general. There are those out there that do provide dedicated systems where you're working directly on the hardware. But what sort of happened at the cloud level was that you were able to just subscribe to, give me a system with, X resources, 4 gigs of RAM, 2 processors, whatever, and they would just spin it up, and you would have it up and running within a matter of minutes. So nothing to install from your standpoint. And then this, of course, enabled, so this is what's generally referred to as infrastructure as a service, sort of the data center cloud. It's where that kind of kicks in. And then that enabled things like platform as a service, where you can just run your application on somebody else's infrastructure without needing any SSH access or anything like that. Sort of the Heroku style systems. And then that, of course, enabled software as a service. So all the Gmail and those kind of things where you're running your software through a web browser, right? So that's basically how we got to where we are today, right? I'm glossing over an awful lot, obviously. But to give you some perspective on this, at the time sharing point, it was academic. So you needed to have a degree in computer science, generally a doctorate, to be able to even interact with these computers in a functional way. You were programming them by punching cards, okay? Paper cards. And you would load a program by taking a deck of these cards and sticking it into a hopper, and it would be loaded into the machine, all right? By the time you got to mainframes, this was on magnetic storage, so you'd have big spools of magnetic tape. That was where how you were storing these things. Getting into the server rooms, we were talking about hard drives, and now by the time we're into the data centers and cloud computing, it's all, most of it actually is in memory these days. But then you've got the flash storage and stuff like that that's doesn't actually have any moving parts anymore. So we're getting a lot more efficient, but we went from having to have a PhD to being an IT, having a degree in IT or something to that effect, to the point now where you might have picked up web development as a hobby at some point, and now you're doing it professionally, but you don't necessarily have to have a degree at all. And in fact, you can click around in the Amazon front end, or the front end that's provided by any cloud provider, and get most of the way where you're going. We're going to see now that as we get into the cloud computing space, there's a number of benefits and associated challenges. And one of them, as we'll see, is actually the amount of effort that goes into it. So scalability is definitely one of the benefits, right? So if you're running a system and it gets, some tweet gets retweeted by somebody famous, you could have millions and millions and millions of hits suddenly. And so being able to turn your one small system into either a big system or multiple small systems definitely is a huge benefit, because you can do that in a matter of minutes, right? Whereas previously you were just out of luck until the traffic kind of went down, which was obviously a waste of an opportunity. The challenge that's associated with that is that since it's so easy to build these systems, it can be very difficult sometimes to control costs. So, we have, for example, 3 or 4 dev servers running at any given time. And one of the things we're considering doing is sticking a little cron job on that at the end of the day, we'll just go through and just turn them all off, right? So we've got the automation that we'll be looking at that would allow that to be a relatively simple thing for us to do. Right now, it's only costing us $100 or so a month in excess cost to keep those things running all the time. But we're not actually using them as frequently as that. So we should be able to shave off about 80% with that little bit of automation there. All right, so the flexibility involved is also really extraordinary. So previously you would have to buy machinery. It would be a huge investment in cost. It would be a huge investment to hire the people who would be able to install and manage it. These days you don't have to cover any of that. So you can just go in and you can build a machine as big as you want at the click of a button. You can put all kinds of interesting network infrastructure in between. Load balancing and all of these kind of things are all built into most of the high-end cloud providers these days. And so you don't need to invest heavily in the infrastructure for this. A Cisco router used to cost $20,000+ sometimes. That would allow you to do things like virtual LANs and things like that. We get all of that out of the box on a lot of these cloud providers. The problem that's associated with that, of course, is that there's a lot of complexity involved. So the more power you have in a system, power in terms of what it allows you to do, the more complex it is to have it do exactly the thing that you want it to do for you. And so that's the sort of the caveat that comes with that. And then back to the HR side of things, as much as we're getting all of this automation in place, it's hard sometimes to get people with the experience and knowledge of how to deploy this stuff in a reliable fashion. Right? It's really easy to go and click through a couple of screens on AWS and build a new VM. Doing so in a way that's going to be reproducible, that's going to be scalable and so forth, does take experience and skill. So that's sometimes difficult to come by these days. Though it's getting better because a lot of the documentation, training, and so forth is available these days that weren't available previously. So let's take a look at some of the actual principles behind this. So the main thing with infrastructure of code is code, right? So you're actually writing this stuff in text files. One of the reasons we like Ansible, excuse me, is because it uses YAML. Now, since everybody here is Drupalista, I would assume, YAML as a file format is probably we're probably all pretty confident about it. I particularly like it because it's so human readable, right? JSON is another popular configuration language for these kind of things. And one of the bigger tools out there is called Terraform. Terraform is by the same guys who make Vagrant. You may have used Vagrant for local development, or Console, or a number of other tools. But Terraform uses JSON. I personally hate JSON as a format. It's great for computers to talk to each other, but for humans, I think it's ridiculous. YAML, on the other hand, allows for really great inline documentation and things like that. So the point is that you want to be able to define the infrastructure that you have in code, and then that allows you to do things like document it inline, right? So instead of having a set of documentation in a wiki somewhere that's talking about the things that you're doing somewhere else, everything is in one place. So this is particularly helpful when you're trying to just figure this stuff out. Ansible's primary, sort of their principle at the root of what they're trying to do is radical simplicity. So the systems that we're going to build with these are going to, by their very nature, be relatively large and complex, or at least there's certainly the potential for them to be to become complex very quickly. Having a system that manages those that's also complex just adds to the cognitive load of trying to figure out how to accomplish what you're trying to do. Ansible keeps that really simple. The way that Ansible works as a general principle is with these tasks. So it starts with a name up above, and that actually is optional, but highly recommended, because essentially it's your documentation for what you're trying to do. And this actually, we'll see a little bit later when we run it, is actually the steps that we're going to see running as we actually run Ansible. So it becomes very easy to see at what stage you're at to track down where that code lives for the piece of code that or the task that may, for example, fail or throw a warning or something like that, to get back to where that is. So keeping documentation in line is tremendously helpful in terms of figuring out how this stuff works and keeping it simple so that you're not having to coordinate your documentation separately from the code that's generating the stuff. Since everything is basically just text files, it's really easy to keep in version control, and particularly easy to diff, right? So you have a complete history. Of course, this comes along with all of the usual things that Git provides, like being able to audit who made what change when. Plus, of course, an additional opportunity to document as you put in your good, useful, descriptive commit messages, right? That we're all doing all the time, right? So anyway, this is useful because it also allows you to do things like branching and all the other good things that Git allows you to do. And to roll back mistakes, right? These things happen, and this allows you to kind of get back to a known good state. And then the other nice thing about it is because all of your code is, or all of your infrastructure is defined in code, you can actually run tests against it regularly, right? So you can build a new VM, run all of your configuration and everything, and then have a test suite that goes in and checks that, yes, indeed, when I hit example.com, I see the front page of the site that I'm building, or whatever the case may be. So actually, before we go on, infrastructure as code is a component in a broader sort of movement these days that is starting to pick up called GitOps, okay? Where you use Git and CI to automate your entire infrastructure. So one of the things that this testing and stuff allows is on a commit, you can run your CI, your continuous integration servers, right? So GitLab CI or Travis or something like that. Not only can you actually test the code, but from there you can trigger all kinds of other external events. So one of the things that we do, for example, is after we've run our tests, we have it send a notification to us in Riot, right? Riot is an open source Slack equivalent. So we get our notifications coming from inside of the CI environment, letting us know if things succeeded or failed. You can trigger a bunch of other things to happen as well. So you could, for example, SSH into a system and run a command. From inside of the CI environment, you could run something on a remote server. Or you could hit an HTTP REST API or something like that to trigger some further event. So say a Kubernetes rebuild of an image or something along those lines. So infrastructure as code is a component in a broader sort of philosophy of trying to automate all the components of what you're doing, so that the only time that you're actually having to sit down and work on something is where there's actual problem solving involved, as opposed to anything sort of rote and repetitive. So getting back to Ansible, so I already spoke to the YAML syntax. So YAML's great. It's descriptive. It's easy to see what's going on. Ansible has, like I say, these tasks, and the way these tasks operate is pretty much the way that you would normally do a task yourself if you were doing it manually. And Ansible, unlike a lot of other tools, just starts at the top of the script and works its way down. And it has all the usual include capabilities and so forth that you see for any of these kind of tools. But it doesn't do things like you see in Puppet, where it's trying to determine dependencies between different tasks. So this task depends on this other task, but they might be written in very different places. And it has to figure out this graph of what order it's going to run things in. That works in some cases. It works certainly in very large cases where you've got a bunch of different people working on things, where you don't necessarily have control over all the code that's going to be running in your environment. However, it's highly complex. It's very hard to figure out what order things are going to run in. If you want to run something after this other task, but before this different task, then figuring out how to get that to happen in a way with Puppet when you're doing anything fairly complex can be very difficult. So Ansible just removes all of that. It's basically like having like a superpowered sysadmin at your side, right? All it's going to do is SSH into a system and run some task, right? So it might create a file, or in this case, it's doing the equivalent of logging into the cloud console for your cloud provider, and clicking through the form to create in this case a Linode VM. So it's very easy conceptually to understand what's going on. So the way it builds out is that Ansible is written primarily in Python. It's built up of a bunch of modules. Modules are generally Python code, but can actually be written in any programming language because they're independently run and just speak to each other through JSON. We as humans using this stuff, as opposed to programmers writing this stuff, generally are going to write roles. Roles are ways of assembling a bunch of Ansible tasks into reusable components, right? So you might have a role, for example, for Nginx, and that's going to install Nginx, maybe write some vhosts for you, and then restart the server, something along those lines. A role would allow you to combine all of that into one reusable bit of code so that for various projects where you're running an Nginx service, you can just reuse the same code and then change the configuration a little bit. So the vhost in one project is going to be example.com, and in another project it'll be example.net. That's just configuration that has to change. The logic of how you want to deploy it, the fact that you need to reload the server after deploying a new vhost, all of that can be built into the role. So that's where your logic happens. And then configuration is basically just, these are the particular settings that I want to use. So we're going to start looking a little bit closer at the cloud components in Ansible. And one of the things that is often confused is the difference between providers and modules. So providers are the infrastructure or the company or the organization that is providing computing services. And then modules, as we touched on, are the code in Ansible that actually does this, that actually executes some of these things. So generally what we're going to see is that there's multiple modules per provider. So provider, an example of provider would be, say, GCE or AWS, okay? There's going to be modules. If you're familiar with Amazon, for example, you've got EC2. EC2 is their computing system, so that's their VMs. But then you also have RDS, which is their database services. So you're going to have modules for EC2, and you're going to have modules for RDS, all within the namespace of the provider, which is AWS, right? So Amazon Web Services. Last time I gave a presentation along these lines, this number was 340. That was 2 years ago. So in that time, we've seen almost a tripling in the number of modules available to run cloud tasks, okay? So we're going to look at some of these in a little bit, but if there's a cloud provider you want to use, chances are Ansible has either has systems that modules that will work with it, or that they're being worked on currently. Actually, before we go on with that, yeah, we'll look at that after. So. Some of the next steps are sort of how this all works in terms of authenticating that it's you, that you have rights to do this kind of stuff. So generally what you're going to do is you're going to download a credential file off of your cloud provider. That's going to have essentially your account ID, your username, something along those lines, and then generally it's going to prompt you for a password when you're doing that initial authentication. We're going to see how that works. That then calls the API, which authenticates your credentials, which in turn then will authenticate or authorize that you can run those tasks. So systems like AWS have very robust policy frameworks that allow you, for example, to start VMs but not delete them, things of that nature. And then that actually then feeds into the actual cloud API that will go and run those tasks, right? So this is a general model that we're going to see in a lot of these cases. I'm not going to touch on it more than this. we're basically going to see this piece here where we just authenticate, and then it knows and then it knows that it's me, and it goes from there, and then we're going to see the other end where it actually builds stuff out. All right, so example time.